on nanotechnology and functional materials. Now we are going to start fourth day and first session. Once again, thank you for joining with us. Today we are having a two resource person for this morning session. Now let me introduce our first resource person, Mr. T. Murugesh, National Sales Manager India and Israel, Amtech Instruments India Private Limited. He has an extensive experience of around 30 years in implementing and delivering growth in wide variety of market segments, example aerospace, defense, optics, and medical field. His expertise lies in promoting and creating awareness on the need of ultra precision machining solutions and vibration control for electro-optics, ophthalmic, and aerospace industry. Prior to Amtech, he started his career with Kirloskar Warner Swazi and has acquired knowledge on machine tool building activities. Later, he had been with Renshaw Metrology as an assistant country manager, handling machine tool metrology, CMM metrology, encoders, and calibration systems. He also worked with Morphus India as a product, and he has developed as a product. And we are honored with your presence, sir. Thank you, sir. Now, let me introduce our second resource person, Mr. S. Velmurugan, sir, Application Manager, Taylor Opson Amtech Instrument India Private Limited, Bangalore. He is currently associated with Taylor Opson Limited, a global leader in the manufacturing of metrology instruments. He is the heading India and Southeast Asia as an application manager for developing new metrology solutions for various industries and research fraternity. He is a mechanical engineer by qualification and holds a degree in business management. He has undergone numerous trainings in various metrology institutes and companies over the years. He has over 20 years of experience in quality and metrology division of various companies. His recent interest includes proliferation of 3D contact and non-contact characterization tools in varied applications ranging from precision machining, optics, metallurgy, tribology, thin film coating, MEMS, etc. Now I request our resource person to continue with the session, sir. Requesting, sir. Sir, now you can start, sir.
Yeah,
I-
able to see my screen?
yes, sir. Yes, sir. Perfect, sir. Perfect, sir.
Okay. Good morning, everybody. My name is Murugesh. I'm Senior Sales Manager working for Ametech under the business unit Precitech, Sterling, and PMC, looking after India and Israel, supporting the requirements of the applications from the customers. First of all, let me thank Dr. Rajesh, Dr. Chandra, Vail Murugan, my colleague, who will be presenting later on. And also it was identified by CMT and requested for us to present about the ultra precision technologies. I assume that the audience here might be knowing what an ultra precision machining means. If not, I would briefly define what is an ultra precision machining means. Broadly classified as since the course or the training that you people have planned is also about nanostructural materials, machining, all these topics somehow correlated for the ultra precision machining as well. We can define ultra precision machining basically as a process where you do a fine machining of the material either by turning, milling, grinding, polishing, or we can also say when we are talking of nanostructured materials as MRF as well as one of the latest technology which we call as polishing as well. All these processes come under ultra precision technologies, and Precitech, where I work, is a machine tool OEM which builds the platform or the machines to generate ultra precision surfaces. When we say ultra precision surfaces, we can also define as generation of nanometric parameters or generation of optical surfaces where the surface roughness and the form means either you talk about figure error or the dimensioning error in the order of few hundred nanometers. So we can define ultra precision technology or machining as generation of optical surface in the order of few nanometers, and to measure it as a figure in the order of few hundred nanometers. I also thought that we should include Taylor Hobson, where Dale Murugan, my colleague, would also take up the session after my completion, because when we say generation of the nanometric surfaces, we also should know there should be a traceability when we say that machine has produced such an excellent surface and the form. There should be an instrument also need to be measured. If not, then whatever we machine becomes an open loop system. So combining an ultra precision machining along with ultra precision measurement becomes a closed loop system and also traceable. That's how I also thought it would be relevant to also include ultra precision measurement system by Taylor Hobson, where we normally or by standard or by default, an ultra precision machining system should be always accompanied by an ultra precision measurement system as well. So today I will be touching about what are the recent developments and the new applications that has come into ultra precision machining. So it could be new to you. If not, I have already defined what this technology means. And you can ask questions either at the end of my session, or maybe if you have some questions which can be explained within a short time, you are welcome as well. When we talk about ultra precision machining, broadly classified its application into electro-optics. I do not know whether the knowledge you have does know about what means by electro-optics, ophthalmic application, precision mechanical components. And where does this go? These are very much required day-to-day activities in defense. When we are talking of consumer electronics, mold inserts, IOL manufacturing. Just to give you an example, everyone might be, I think 99.9% of the audience here are using mobile phones, for example, or you watch the TV at home, and maybe a large TV, flat screens and all. All these devices have an ultra precision machined component. You'll be surprised. How does this come into picture? Is, for example, you know that your mobile phone has a camera. Camera also has lens in it, and these lenses are not machined. These are molded lenses, and the molds are manufactured on ultra precision machine. When you also talk about the flat panel TVs, whichever you see about LED flat panels, these panels or the screens are rolled on a drum roll lathe, where you can also have a very small features where the electronics go inside like LEDs. That's how the flat panel LED screen are also rolled, or the drums are manufactured on ultra precision machine. Further, the application also gets extended to LED lights. When we talk of an LED, the LED molds are also done on ultra precision machining. I do not know whether you have heard about head-up displays. For example, I would say whenever the pilot is in the air, fighter aircraft, he need not to look at the dashboard, at what altitude he is flying, at what rate of climb he is climbing up. So the data of the dashboard needs to be reflected onto his windscreen. That's done by a head-up display. These are again the free-form applications. Likewise, you can find so many of applications which are challenging, maybe new to you, but this applications and the requirement has started in India, and we as an AMETEC, along with Taylor Hobson, we support the Indian customers. When we talk about ultra precision machining, you are seeing on the top left-hand corner on the slide called as diamond turning. So this doesn't mean that we turn a diamond. We use a cutting tool. You know that whenever we are talking of a machine and producing the component of the desired figure and desired surface quality, you need a machine to cut the material, and you need a spindle, which you're looking on the second image, and you also need a part or the component, and you need a tool to cut the part. So when you're looking at the tool on the bottom left-hand corner, you can see a small triangular shape, which is a diamond tool. So that's how a basic ultra precision machine will be a diamond turning, basically a two-axis. So what it does is, you know that any tool has got its own radius of curvature. So whenever you are machining the part, it produces the peak and valley. And when we are talking about this peak and valley, ideally speaking, if there is no radius on the tool, the surface what you're looking here like a waviness should look flat, perfectly flat. But it doesn't, because you know that any tool that we produce has definitely a radius. We try to utilize as much a small radius of curvature. So when we do a machining or remove the material from the part, you also have a peak and valley, and also a shape right from the start to the end part when you machine. That's called as the form. The form can be spherical, aspherical, it can be diffractive like segmental, it can be toric, for example, having a major and minor diameter in whichever axis you want. And you can also have so many parts on the spherical surface, which we call as an off-axis shapes or the parabolas that can be done on the machine. So these are called the form. So if you look at the right hand corner, the machine is capable of producing the smallest peak and valley when we talk about the surface finish, less than 1 nanometer. And when we talk about how much is the form accuracy, when we talk about the figure error, what was the target, it can produce up to a level of 0.1 microns, or we can also define as 100 nanometers. If you have any doubts here, you can just ask me any questions, or I'll move to the next slide. Am I audible?
Yes, sir. Yes, sir. Clear, sir.
Okay, thank you.
Yes.
Historically speaking, this diamond turning or ultra precision machining catered to the applications of mainly what we call as night vision and thermal imaging. Anybody knows about these images, what it means? Have you seen these kind of images anywhere else earlier? Anyway, you know that the normal camera or your mobile phone camera can take the images only during the daylight. And if the daylight goes to zero, or example, I can say the light is absent, it becomes absolutely pitch dark. As well as when it becomes pitch dark, and if somebody is moving in those areas, your camera would not record any kind of images. So the diamond turning here, when we say about night vision and thermal imaging, it catered to a material where we can use those materials called as infrared crystals. These are the materials that are responsible to create or allow these infrared rays to pass on to that material called as germanium, silicon, whatever you call silicon carbide, aluminum, for example. All these kind of materials which come under IR crystals are the materials which works as lens. These are not plastic lenses or transparent lenses or a glass lenses. These are called metallic lenses. I think you might be, these terms are new to you. So these IR crystals, you can log onto the website. You can get so many materials, zinc selenide, zinc sulfide. These are the other materials which are used in night vision cameras. So what this does is whenever there is a movement in the environment where there is absence of light, it captures the image, how either each of the material or the moving on object has got its own thermal imprint. For example, human body has got its own body temperature. So the IR infrared frequencies pass on to our body, and there are detectors which detects, and it forms an image of the person moving around. That's how the night vision and thermal imaging devices were found, and these applications are used for border security force. For example, when we are talking of Pakistan and India, border security tensions and all the soldiers have Google goggles which are mounted onto the helmet, where they also have a small screen in front of them monitoring the border. If there is any infiltration that happens, usually at night, they can find the people at what distance they are, and who are moving across the border, and that will make our nation much more secure. So this is how the infrared materials or the IR optics using IR crystals, which are machined by Diamond Sun. These are some of the images of germanium, silicon, zinc selenide. Those are the lenses that are done on this machine. It looks very shiny, and you people might be thinking that, oh, this cannot be turned, and these are not the machine items, these are polished. But for information, these are not polished lenses, these are diamond turned. These looks like polish free. For this, you need basically 2-axis diamond turning. If you look at the left hand bottom side, you have an x-axis, z-axis, the movement slide, and the spindle, where it also has got a positioning system, and the machine looks on the right hand bottom corner. It's called as a diamond turning machine. What are the applications where all these are? You can see infrared lenses. These are used also on the missile launchers, where you need to fix the target at night and fire. There are LED displays which also go on backplane of the flat panels. The lens arrays, when we talk about lens array, there are multiple lenses over an area. It could be circular, it could be spherical, it could be aspherical. These are the lens arrays which also can go onto the automobile headlights as reflective materials as well, where you also can make micro prisms, definite structures. For example, all the tail lamps, for example, on the automobile, are also molded components, or the acrylic material, which also has a definite pattern which reflects the material at night, like the tail lamps. We also have an application where the hard disk is placed between the lapping plates, and we also make the lapping plates diamond tone. Mobile phone cameras, I already explained to you. Optical molds for LEDs, diffraction gratings. This diffraction gratings goes into the space. We have so many applications delivered and in action with the Laboratory of Electro-Optics in Bangalore, Space Application Center in Ahmedabad. We are also working closely with VSSC and IISU in Trivandrum as well, where these applications are very, very crucial. Showing you an image where the component is mounted onto the spindle, where the tool is also turning a material on a tool post. This shows you basically a 2-axis diamond turning machine. Moving from 2-axis, we also have an applications where we extended from basically 2-axis to 3-axis, where we have an X and Z, the linear motion, C-axis in the circular motion, and we extended using these 3 axes. We also developed another application or an accessory, which also called as an FTS. It's called as fast tool servo, and also we also developed to integrate on the machine as an accessory called as a very high ultra precision milling spindle as well, which is on the right hand side top. The blue color is called a very high precision milling spindle, the top one and the bottom one. So fast tool servo means it's an oscillating tool over the Z-axis slide, and it oscillates with a definite interval, moving and cutting the metal at a particular angle of the rotational axis. Becomes a little bit complicated. When I showed you here, uh, lens array here on the circular surface, you can see the small dimples. These are called arrays. Creating this program on a conventional or the existing available CNC turning center is very, very difficult. So using a fast tool servo, as I explained, showing this as an oscillating tool, creating the feature on the circular surface. Now, this shows, for example, a diagram where you have a machine which is also having a fast tool servo application, which is used to make cell phone cameras. When I say cell phone camera, we don't produce one lens at a time. If you look here, this diagram shows you each one cell is one lens. So we make a mold which looks like a honeycomb structure, which should be male and a female, and the geometry is defined depending upon the designer of the optics, and based on the size of the optics, the surface area is defined, and we program this onto the machine where it creates so many lenses. So when you do an injection molding of these lenses at one shot, there could be lenses of 3,000, or maybe sometimes it can go up to 5,000 lenses for one injection molding lenses. So why this is important and useful is when we are also talking about ultra precision, this makes cell phone cameras higher in quality, and sometimes you people also look what's the zoom available. When we say higher quality, higher pixel, higher resolution, and it's also better in low light. So if you look at the mobile phone camera, the guy who is holding the lens housing has got so many lenses inside. It could be up to 6, sometimes it could be up to 8. So there are 8 lenses housed in this small device. We are hoping about this technology coming to India. I think Apple may start manufacturing these as well in Chennai as well. And we have those lenses, molded lenses are done on our machine. Here it is showing you a video where this is an oscillating tool oscillating at very high frequency, and where you're looking is a mold. It looks like a honeycomb structure, where you can see each lens has got a definite shape, geometry as per the designer. So this program runs maybe a week's time, a week's to 10 days time, on a very tight temperature control in the room. Moving on to the next technology, or the extension of the machine platforms, we started adding more access to the machine. When I spoke about X, Z, C, and the fast tool servo, we also added a Y-axis. For example, X, Y, Z for you may be basically a machining center. When you want to define as a thumb rule. These machines are also called as freeform when it comes to an ultra precision machining, where you can develop your own surfaces with a definite geometry with the equations, and the freeform is generated. So you can see here the machine also doing a LED reflector onto the lighting industry. The new applications are, like, as I mentioned to you, like LED reflectors. If you look at the brass component here, you can see there are small grooves, and these grooves are not parallel. They are meeting definitely at the center, and the grooves are becoming wider and wider as it goes to the periphery. So these grooves are maybe in the range of 2 to 3 microns, and these are molded, and you see these reflectors are the finally output of the component when you make the molds, and these LEDs are housed inside. For example, you might have seen in today's theaters, for example, or in malls, for example. There are LEDs which project so much of bright reflections. So more the geometry and the reflections of the mole, higher is the output of the light, which is measured in terms of lumens. So ultra precision machine also makes LED reflectors, which also gives better light output as well. This shows you how the grooving is done, which we are machining on a freeform machine. This is a cutter which is making those grooves, and you can also see that this is the B axis moving after once the machine is cut. Can you see the small grooves here? These are in the order of 2 to 3 microns and has got a definite geometry. So this machine is basically a 5-axis machine, X, Y, Z, B, and C axis. So this is a machining of a LED reflector mode. I also touched when I started explaining to you about how we classify the ultra precision machining into electro-optics and ophthalmic business. So I will be touching today most probably on the electro-optics, where one of the applications I explained was the head-up displays. Here the diagram shows you the bottommost. This shows you the application of head-up displays in automotive segment. We are yet to adopt this technology. Right now, this is very much popular in France and Japan, where when you're driving on the highway for longer drives, the driver gets fatigued whenever he wants to look at the dashboard, at what speed he is moving, at what rate of the engine RPM is, and whether the fuel is getting over. All these kind of data, every time he has to look down. So the automotive industry also has started adopting this head-up displays, where you can find the data. All of the dashboard display will be onto your windscreen, so you need not to look down while driving. This also gives you maximum safety while driving on the highways. Similarly, applications on the fighter jets, on the aircrafts as well. The pilot needs to know at what angle he's flying, whether he's flying incline, at what rate of climb he's climbing or diving down, at what altitude he is. So all the dashboard of the data on the pilot, Air Force pilot, on the aircraft also needs to be projected on the windscreen, which is very important because he doesn't have any time to look down and take actions. So this also has played a very, very important role of creating the freeform head-up displays onto the aircraft as well. I think we have this application in India. We have there is a company, I would say scientific research company under CSIR based in Chandigarh, who have developed the head-up displays for the Indian aircraft fighter jets in India. This video shows you an example of a freeform head-up display mode. You can see it's a brass, and I explained to you about the fast tool servo or the oscillating tool. It is moving in and out, it's oscillating, and definitely it creates a surface or touches the component or gets in contact with the component at a definite degree programmed by the optical designer, and we program this on the machine. Looks very simple, but it's very, very tough to program. But Precitech has developed the software for developing these kind of features in the machine itself. Programming these on a normal conventional CNC machine is really, really difficult. Moving on to the next application of the ultra precision machine is a drum roll lathe. I explained to you what's the importance of the drum roll lathe, but in India, we are yet to pick up this technology. Most of these drum roll lathes are very, very popular in Korea, Taiwan, Malaysia, for example, where most of the flat panel TVs or LED screens or flat panel TVs are imported. Sorry to say this, India is not yet geared up to manufacture these, but most of these applications of drum roll is found its presence in Korea, Taiwan, to some extent in Singapore, Malaysia, and all. So if you look at this, it looks a simple drum, which is a copper drum. On these, there are microstructures, which could be grooves, or it could have microprisms, or it can have a definite pattern when we are talking of light bending, when we are talking about making some holographic stickers, where these people use for their patent of the product as well, where we call as light bending or light reflections. So these applications are mainly focused by the drum roll application. So you can create any kind of microstructure, grooving, microprisms, or definitely a pattern what the customer needs. So if you look here, it's a granite bed. I do not know if I have some time. I would also like to touch on vibration control. These machines are usually housed on a granite bed, under which there are isolators, where it also lifts the whole granite bed onto the isolator, because we need to have very, very minimal vibrations on the floor. So this vibration control eliminates the floor vibration, making the top of the machine absolutely vibration free, which is very important. So what this does, for example, if you look at the drum roll, has definitely a pattern here. When we are talking of the pattern, these are small grooves on this. And what this can be done is whenever the older, what we call as the TV, where the tube version. When we are talking of tube version, if you move your viewing from an angle, you couldn't see any images. So, and also if there was the light falling onto on the screen, which was a picture tube, you couldn't see any images. And also now there were a limitation of the tubes not getting bigger and bigger, because the manufacturing of the picture tubes was challenging. So with the introduction of flat panel TV, today you have 100-inch, 120-inch, sometimes you see so many long meters, maybe even 10 meters, for example, screens on the advertisement board on the highways. You can see so many LEDs, flat panel screens and all. All these were possible because of creating large flat screen TVs, which was possible by using to manufacture on the drum roll. Moving on to the next application from the drum roll, we also developed a new machine model, which is called as micro groove generator. As the definition itself states you that we make micro grooves. So it doesn't also limit only to make grooves. It also can be used to create micro prisms as well, like conical shape. It could have a polygon shape, whatever is possible. So if you ask me where these are used, I believe maybe you might have traveled in the airport during the night time, where you have people wearing these safety jackets, where whenever their light falls on it, the right light reflects on the jackets, because at night the airport guys, support guys, or the field guys on the runway needs to guide the pilot, and also the transiting of the luggage from place to place, or from the aircraft to aircraft, needs to be identified, which is very important. And also sometimes, I do not know how many people have you observed that when you're driving on the highway, there are signboards, and when the light, the headlamps light falls onto the signboards, the light never reflects back to you. Otherwise, it will be a pathetic situation where you would be blind while driving, and there's a possible of an accident. So these signboards reflect the lights away from you. Similarly, the jackets where the guys on the support either it could be on the road safety guys, or on the airport safety guys, or maybe somewhere where there is no light. These jackets are worn because you need to identify there are guys at night working. These are having micro grooves or the micro prisms. If you look at, this is one of the material where we talk about the reflective material, and each one of these segment has got a definite geometry. That means if you incident the light perpendicular or any angle on the structure, the light never reflects back to the source. That means it the light reflects away, not incident onto your eye. So that's the technology here. And these micro grooves or patterns or micro prisms are done on this micro groove application on the micro groove generator on this machine, extending to the next platform. We also had one application where we have shot one video here. I have been talking about machining. If you look at, this is a slow motion video. This is running at 60,000 RPM, shot on slow motion video on our vision research camera, which is called as high speed camera. You can have a look at it, that it looks like it's moving very slow. Sorry, it is moving at an RPM of 60,000 RPM. And we have captured how is the chip flow. You can see the chips flying out. And this is a milling tool creating the surface onto the machine. So this is also a product of AMETEC under ultra precision division. Sorry, it's not ultra precision. It's coming under high speed imaging or high speed camera as well. When I say about ultra precision technologies, I explained you about the Precitech. Sterling, I thought that it's not very much important. The main difference between the Precitech and Sterling is the Sterling machines are used mainly to cut the plastics, usually used in the manufacturing of intraocular lenses. I don't know how many of you know about intraocular lenses. People develop cataract over a period of time when they age after 40, 45, 50 years. And the human eye tends to develop cataract, and the lens needs to replace. And these lenses are replaced by an artificial lens. And these lenses are produced on Sterling machines, which are mainly used to produce contact lenses. I hope you know what a contact lens means. Some people don't like wearing the spectacles. They would like to use contact lenses. These contact lenses and the intraocular lenses, which are used to replace the human eye by intraocular lenses, are done on Sterling. We have a quite good number of machines in India, to an tune of 100 machines. To name some of them are, for example, in Madurai we have Aurolab. We also have some some OEMs or the manufacturers in Baroda called as Care Group, and we also have one major customers OEM in Chennai called as Apasani Associates. And I explained to you that these machines are very sensitive to vibration as well, and these machines default come by vibration isolation systems as well on the machine. I believe that maybe being an engineering college, you might be having some of the optical benches, or you might be having scanning electron microscopes or a transmission electron microscopes, where you might have been using the vibration isolation table. I'm not sure what brand make, but TMC being an ISO 9000 certified company, we produce one of the best or the global leaders in making the floor vibration control system. Name it for confocal microscope or a microscope, very high resolution, It can be electron microscope, it could be scanning electron, SEM, TEM, or a STEM application, where if there are floor vibrations, you don't get the imaging. Also for optical test bench for laser applications, optical test benches, where we talk about the optical tables, which are also very much important. I also have worked very closely with so many OEMs in India and supporting their application requirements. We also do the site surveys for the machines where these instruments need to comply to the floor vibration specifications. Before going to the next topic, there are these 5 divisions. One is called Creaform, where we also make 3D measurements and reverse engineering, where you need to identify the data of an unknown surface. Rykert goes into medical, that doesn't really come onto this manufacturing. Solartron metrology are the small LVDT gauging probes, where you can use these LVDTs for any linear measurement or gauging a feature in terms of gauging a diameter. Taylor-Hobson, again, my colleague Vale would talk about how the high precision or the ultra precision measurement is very important when we talk about only machining. It will not be an ideal way of only buying a machine. So bundling with an ultra precision measurement makes sense. Over and above, we also have a division called as Zygo, which is also optical metrology equipment. Whenever we would like to certify a product, after measuring, some of them would always demand on how do I measure a full 3D map of a particular feature. For example, Taylor-Hobson has an equipment where it takes a single trace, and it can also take a 3D trace. But most of the time, taking this 3D map with the full 3D trace would be much more cumbersome. There are ways of non-contact metrology as well, where Zygo comes into picture, which takes the full 3D map of the surface using laser interferometer called as Zygo. So all these together gives a complete solution to the customer, where he need not to go for a different vendor to identify how do I measure, how do I manufacture, what is a contact metrology, what is non-contact metrology. You can have all these products under one roof, where AMETEK can support any of the engineering industry, engineering college. We are also supporting IITs, for example, for academia as well. So how much time we have now, Dr. Rajesh?
Sir, you can proceed, sir. We can take because other resource person time we don't know, sir. You can take, sir. Still, we are having more 1 hour more. 1
1
hour.
hour more. No problem. So I will now also go into
Yes,
more.
yes.
Thank you. I will now go into a little bit more elaborative on the global perspective of diamonding. That means, what are all the applications? Because when I started Precitech to pass on the technology, educate people here, it could be academia, it could be R&D, it could be defense and aerospace. The technology was not available. So people used to say, why should I buy diamond turning? Where do I find the market? How should I set up? We do not have human resource. At least for these past 10 years of my experience in AMETEK for Precitech, at least now I'm able to say that I'm a little bit confident now with the technology available here. People are now started looking into why shouldn't we go in to for ultra precision manufacturing technology, develop their own process, and benchmark themselves as a competitor to the global level. So people started asking me that, what are the people doing globally? How you people make so much of business? So at least now we are here in India to state about, okay, we are now here to support you and what technologies are available. And we are here to also help you in develop those these processes as well. So Amatec ultra precision technologies are not here for selling. I reiterate again, we are not selling here. We are working and catering to the application requirements or the pains of what the customer has. That makes customer very much confident to remain with us, because these technologies are not available everywhere. We are having a very few uh, vendors that can supply to these. So then moving on to the application requirements, I explained to, we had 2 axes, 3 axes, we had fast root servo, we have a micro groove generator, and we moved on to the 5-axis machine. The applications became more and more challenging because the customer also started demanding more and more. Even with looking at the mobile phone cameras, earlier you had 8 pixel, then it became 10 pixel, 14 pixel, 24 megapixel, 32 megapixel, 64 megapixel. The electronics became shorter. Even the lens housing housed more lenses. So they demanded new machine platform, new accessories, and we also needed to develop new softwares as well. Only developing the machine doesn't help. You also need a software to develop such kind of components as well. Also, not only developing the software, we also have to have new applications on board, and the metrology methods, what we had earlier, also required more changing of the machine configurations of the metrology also. Over and above this, there were materials which were challenging and not able to diamond turn on the machine itself. So there were new materials coming into picture as well. And one of the most challenging were glass. And glass, people normally talk about grinding and polishing. But now with help of a new technology, we can do the diamond turning of glass. But the question is, you may ask that, oh, you can do the diamond turning of glass, but it is limited to preforming of the glass before grinding, because preforming is one of the toughest and time consuming for any of the glass polishing or grinding. So it becomes very challenging when we are going to preform the glass as well. So I explained to you application global requirement is the new technology, or the demanding application is again VR and the AR. So if you're looking at augmented reality, virtual reality, when we're talking, then we have our applications in electronics, semiconductors, ophthalmic, infrared, semiconductor science, technology, defense, and aerospace. We came across the new fast root servo, which I showed earlier was on the older segment. We have come across the new one, where you can look at the continuous acceleration mode. About 40 G is the oscillating frequency of the fast root servo. So it looks very simple, but whenever you want to program, these are the one of the applications where we have developed on our own. It's our own design. When we talk about the earlier, the travel, here you look at 5 mm of travel. Earlier we had only limitation about 1 mm. Now we have extended it to 5 millimeters of the travel in and out, and create the surface like lens arrays, torics, micro grooves, or whatever we talk about. Moving on to the next application, there I also mentioned you that the ultra precision also catered to the aerospace industry. When we talk about aerospace, you also might have seen sometimes on BBC or in CNN. I do not know about India much of the time. You see satellite maps showing a particular area, how the weather forecast is there, for example, in Trivandrum or in Tirupati. For example, whether it's cloudy or whether it's rain. So at that time, you need to focus the camera to a particular angle, latitude, longitude, and the camera has to focus. So at that time, the lens and the housing has to be perfectly aligned to this optical center and the mechanical center, and this needs to be very, very perfect. Otherwise, if the satellite orients the camera maybe to India, then it could focus Pakistan, for example. So that's the level of the accuracy we are talking here when we talk about lens centering. When we say opto-align, this means the center of the optics and the center of the lens housing should be almost zero. We cannot make it zero, but almost zero. It has got a perfect tolerance as well in terms of angstrom limits. So that's how we can also provide one solution where we can center the lens and align the lens to the optical center and to the mechanical. We also extended our applications using a device called as laser assisted machining. This guy is from one of the university in Michigan. He's spin off from one of the technical university. He's an Indian. Very proud to say that, Deepak Ravindra, who developed a patent using laser. He tried to also machine some of the challenges of the materials which were harder. To some extent, when I say diamond turning was majorly known to machine non-ferrous materials only. But with the technology available now, with the laser assisted machining, and the another one is called as Sonex. Sonex is a company based in Germany where it uses ultrasonic assisted machining. It has an oscillating tool which oscillates to ultrasonic frequency, and utilizing the tool to remove the material, which can be used to use the harder materials as well. So we today we can say that whatever the materials that were not possible to machine with diamond turning also has been extended to the harder materials. For example, hardened steel, 52 as you can see here. The size is 230 by 110 millimeters. This shows a head-up display free-form shape. Steel looks like a mirror, which is done using ultrasonic assisted machining by Sonex. So if you look at the machining hours here, roughing and finishing, roughly it takes around 15 hours, for example. And if you ask me what's the feed rate, sometimes like roughing and finishing, 30 microns per meter, and 20 microns per meter is the feed rate. Also, there are certain features. For example, if you look at the steel, there are small dimples here using the ultrasonic assisted machining. And this shows about the microstructures using the steel again. It's a basically freeform surface. You can either create a lens array, you can create a waviness waveforms, or a particular wave defined by a particular geometry. You can make small microstructures as well. If you look at here, these are small microstructures as well. What are all the other materials that were possible? Earlier, these were impossible to do diamond turning on the machine. Hardened steel, Invar, for example, nickel alloys, calcium fluoride. And we are also now able to do a machining of ceramic as well, like tungsten carbide as well. Fused silica. Fused silica is a material which has got zero expansion at the higher temperature as well. These fused silica components, like gyroscopes, goes on to the satellites, space satellites as well. So if you look at for example, this shows you a tungsten carbide where the diameter is 10 millimeters. You can see we have created an optics surface onto this material. So if you ask me, there is a principle where how it is possible to remove the material for the ceramics, hard ceramics or hardened steel, for example. What happens is, if you look at this as a tool, the yellow part shows you a diamond tool, which in which there is a process, there is a micro groove of the order of maybe 0.1 to 0.5 diameter, and the laser is passed through this diamond tool or the orifice, and this diamond, the laser is incident onto the surface. And what happens here at this surface, the material becomes soft. So when the material becomes soft, the diamond starts removing the material, makes this area machinability much more easier, which was almost impossible. So you may ask also, is Murugesh, when we use laser onto this material, does the material property change, or the figure also may change, the shape of the component may change? The answer would be no, because the technologies is developed in such a way that it creates almost no heat. Definitely there will be a heat, but it is almost no heat, keeping the material intact. There is no deformation of the material property, no change in the shape of the material. So this is one of the advantage of using the laser assisted machine. So how did we extend our applications? Infrared materials is zinc selenide, silicon, calcium fluoride, zinc sulfide, barium fluoride. And in 2018, we extended our applications to tungsten carbide, again, which is a very hard material. We have given a machine to one of the ceramic research institute in Calcutta, where they are using our machine, using laser assisted machining to make a tungsten carbide mold, where it is used to make an aspheric glass lens as well, because creating an aspheric glass optic is really challenging. So this has made possible now, and this technology is available in India now. In 2019, we were able to also machine steel for head-up displays and also for germanium. Now in 2020, we were able to diamond turn glass. So these are some of the application and how much was possible in terms of, for example, the surface roughness for silicon diffractive was 3 nanometers, and the figure error was about 150 nanometers. Zinc sulfide, we were able to get around 1.2 nanometers, 1 to 10 nanometers, and the form accuracy was around 200 nanometers. Earlier, this was impossible to do it on a diamond turning machine. So applications on tungsten carbide, I explained to you, is to use laser assisted machining, and very much helpful for the people for using glass optics, using molding method, using tungsten carbide. Applications in glass, how diamond turning is useful. I think if you look at the subsurface damage. So what do you mean by subsurface damage? Is whenever you have machine a glass, either you go for a grinding or a polishing or MRF, for example. MRF is the last process when we talk about the polishing. Is the glass undergoes a stress. It's very much brittle in nature. So what happens is whenever the grinding wheel touches the surface, it creates a damage over the surface. That means it produces cracks below the surface, which we call as subsurface damage. And in a grinding application, the surface damage would be around more than 20 microns. And when you want to make an optics, for example, or a lens or any feature, for example, these need to be polished or ground to this level to remove the subsurface damage. It takes hell a lot of time, maybe days together, to remove this material. So with what happens in a micro lamp, if you look here, the surface damage created on a glass surface is less than a micron. So it becomes more simple, also significantly reduces or minimizes the polishing time or the preforming time. So for example, sometimes you also would ask, what would be roughly the surface roughness on a glass material? So if you are talking here SA is nothing but the whole surface area. We always define somewhere between 10 nanometers surface roughness. But when we talk about the optics on the glass, some people would demand more than, it could be sometimes 0.1 nanometers, or sometimes it could be 0.01 nanometers as well when we go for the optics application for space. But using a diamond turning, you are going to eliminate this, and it greatly, significantly reduces the polishing time and the pre-grinding or I would say, preforming of the glass application. So we can also machine BK7 glass as well. There are some of the BK7 sample, and with the interferometer based, we were able to also identify what was possible in terms of measuring the BK7 glass as well after machining with microlam as well. Few silica is again the whatever the surface roughness was achievable by diamond turning using the microlam was around 30 nanometers. It's good, which makes very simple in terms of process setups for these space applications when they wanted to use for grinding. Diamond turning has significantly helped them. So if you need for the most of the current information on Precitech, Sterling, on vibration control, you can visit our website www.precitech.com. And if you have anything to ask, feel free to write to me at murugesh.timman@amatech.com. I would be able to help. One of the strategy of Amatech I would try to stress here is we help. One of the strategies we help and educate the engineering colleges, universities, and educate people in terms of bringing the technology and the education level to the current level. What is available onto the global requirements, or what's the global perspective, and how we should be able to compete with the global technology available in the world. So I would end my session here. So I would leave maybe another 5 minutes silence, or maybe you can ask me some of the questions that might have come up during my presentation here. And I would thank Dr. Rajesh, Dr. Chandra, and the audience who are there, and also thank Very Murugan, CMTI also, because they identified me and requested me to cater my knowledge to the team here. I hope this would be helpful for you, useful for you. Maybe in some time, maybe I think the time is short, I do not know. I would have touched even vibration control, which would be important. Or maybe you can invite me for any future requirements, or if there is a possibility, I would also present myself on TMC, which is an environment control when we talk about vibration, electromagnetic induction, reducing the EMIs by offering you the solutions. Acoustic chambers also we provide when we are talking about acoustic control in the room as well. So thank you very much. If there are any questions, I will be happy to answer you.
Thank you very much for your excellent presentation, sir. Now I request participants, if you need any clarification or having any doubt, you can unmute yourself. You can ask question directly to our resource person, or you can type a question in chat box. Sir, one question in chat box, sir. Shall I proceed, sir?
Yes, sir. Yes, sir.
This is from Professor Yogesh. Sir, how outside new scholars can come to, sorry, sir, this is a general question, it seems, not technical. How outside new scholars can come to AMTech for research work, or whom they contact?
You can write to our HR, for example, if there are scholars who would like to do a course. For example, we as I mentioned to you, we work with closely with one of the universities near Tanjore. I'm not sure.
Yeah, that is near Tanjore.
Yeah, we take people or the research scholars who would like to do it, and if our HR and engineering team, the vice president of engineering, will go through the profile, and if it looks relevance to our requirement, then definitely we would take them on board, maybe for a project base, or maybe there are a lot of IoTs available now, and if it becomes value additions for Amatech, we would take them on board on a training purpose or on a project purpose. And if found suitable and if things works well with the new project assigned, I think they will be on board as a permanent employee as well. There are a lot of examples as well in AMETEC as well. Does this answer your question?
Yes, sir. Yes, sir. Thank you, sir.
Okay. Yeah.
Now, I request dear participants, please, if you need any clarification, please unmute yourself, or you can type your question in chat box. Sir, just I will give you a vote of thanks with a few words, sir. Then we will start our Velmurugan sir to continue the session, sir.
Good, sir.
Thank you, sir. Thank you. Thank you, sir. Just 1 minute, sir. Thank you for your wonderful presentation, sir. Your presentations added more value for this short-term training program. You have explained the application of latest technology assisted machine tools, how the latest technology is useful for the humankind. Really, it is excellent presentation, sir. You have given the enough knowledge regarding ultra precision technologies, and the takeaway from your presentations are very high. For example, ultra precision measuring system in precision machining and ultra precision machining, a new application and recent technologies you have explained, and dimer turning and historical application like night vision, thermal imaging, how it is working, infrared crystals like metallic lenses, image using thermal imprint and IR optics, and fast tool servo, example lens array, cell phone, camera lenses, and particularly free-form ultra precision machining like LED deflectors and free-form head-up displays on windscreen in automotive and aerospace, ultra precision drum roll L, and application in flat panel TV and LEDs, and Precitech TMC Sterling machine useful for contact and intraocular lenses, and floor vibration isolation system, and global perspective diamond turning applications, and fast tool servo 5000 lens centering with opto alignment, and micro turning extender, micro laser assisted machining, and Sonics fully integrated steel applications, freeform surfaces like other materials also like Invar, titanium carbide, fused silica, nickel alloys, and finally you explained the grinding and laser assisted manufacturing in laser assisted machining in fused silica and PK7 glasses and tungsten carbide also. Thank you, sir. It is a really excellent detailed presentation, sir. Now I request our second resource person, Mr. S. Velmurugan, sir. Please, sir, please continue with your session, sir.
Just before ending, Dr. Rajesh, there is Nehal Joshi mentioning in his chat box, mentioning about
yes, sir, there is a question, sir. Please, sir. Yes, sir. One more question.
Yeah. These, when we talk about coating, this is a process not related to diamond turning. Any surface that you generate is an optical surface by a diamond tool. When these surfaces are created, these surfaces needs to be protected not only against a human touch, it should be protected against the environment, or when you know that whenever we are also talking about aerospace, when the satellite is in the space as well, there are so many gases in the space as well. So the surface needs to be protected. So a coating is a different process of deposition of an anti-reflective material onto the surface. So anti-reflection coating is not coming under diamond turning. It's a process where there are so many manufacturers of making anti-reflective coatings. You place the lens in that coating chamber, it gets deposited, and that's how the surface is protected. So that's a different what you call process altogether. Does this answer your questions, Nehal? Okay, thank you very much. Thanks everyone. Please get in touch with whatever doubts you have. I would be able to answer you. I hope you have noted down my email ID. If not, Dr. Rajesh or Dr. Chandra have my contact details. You can reach me anytime. Thank you once again. Bye-bye.
Thank you, sir. Thank you.
Sir, good morning, sir. Sir, good morning, sir. My name is Chandrasekhar Reddy.
Yes, sir.
Sir, good morning, sir. Myself, Dr. Chandrasekhar Reddy, convener of this program.
Good morning.
Thank you very much for accepting our invitation, sir.
You are welcome, sir.
Sir, on behalf of management, principal, Department of Mechanical Engineering of SUPE, and the participants of STTP, thank you very much for accepting our invitation and delivering an informative and thought-provoking webinar on ultra-precision technology, organized by SUPE College of Engineering, Tirupati, in spite of your busy schedule. Thank you very much, sir.
You're welcome, sir.
Also, I am also thankful to the Narendra sir who has given your number and who has connected with us. Thank you very much, sir.
No problem, sir. You're welcome anytime. Bye-bye.
Thank you.
Thank you, sir.
Yeah. Good morning, everyone. I'm audible.
Yes, sir. Yes, sir. Yes, sir. Audible, sir, and PPT clear, sir. Perfect, sir.
Yes. Once again, thank you very much, Dr. Chandrasekhar Reddy, Dr. Rajesh, and other organizing committee people. Thanks for your invite to myself and Mr. Murugesh. Thank you, Mr. Murugesh, sir, for the detailed presentation. I would say it is not very detailed. It's a glimpse of the latest technology. Murugesh definitely, he can able to talk each application more than 2 hours, I'm sure, because we used to present jointly with many seminars or many webinars. So we have collected a lot of technical information, but it is just a startup. So for the academia perspective, so we are ready to present or ready to participate with your future programs. Probably time comes in. So I'm going to talk about the measurement solution what Taylor Hobson provides for the ultra precision technology. So basically, Taylor Hobson is a UK-based company. This is 133rd year when Taylor Hobson starts. So which means they have a very rich history and background. So technically, very superior company. We have our latest trends in technology for the contact and non-contact solution we provide to the optics industries. So most of the time we give a joint solution to the customer along with the Precitech diamond turning machine. So it's a closed loop system. So which whatever the component we produced high accuracy part or high precision optics, which can be measured, which the instrument measuring instrument will be next to the manufacturing or diamond single point diamond tool machine. We can measure it precisely, and whatever the form error, it can be corrected by getting the feedback from the measurement machine and then give a feedback to the manufacturing machine, so that within 1 or 2 iterations we can able to correct and we can able to achieve the desired results from the manufacturing machine. So that is why even Murugesh presentation, he keeps saying it's a closed loop system. Manufacturing along with the measuring equipment, it is meeting together and produce the good results or expected results for the customer requirement. So I'm going to talk about mainly the 2 measuring instruments. One is from contact, tactile measurement, and another is a non-contact measurement. We provide both the solution. It depends on the requirement from the customer. We offer both, like optics solution. We offer contact as well as non-contact both. So PGI is the phase grating interferometer, is the contact based machine. The contact, the probe or stylus, it is made up of diamond. You can able to see it in the left hand side picture. So the stylus is going to touch the part and it moves along with the surface axially, and it picks up X and Z coordinate when it moves. So the X and Z coordinate will define the surface quality or the form quality. The software will combine all the points, collective of points, and it takes roughly about 8,000 points per millimeter. So if we are measuring like 50 millimeter, we have thousands of lakhs together points, and the software will process it, and we can able to get very accurate results of surface finish, surface quality, or the form measurement. And the second one is the LUFO scan, which is non-contact based machine. So anyway, I have a measurement principle video of both the techniques. I can run through in the later slides. Yeah. So the PGI is the leading capable, very high precision measuring equipment in the contact based. So example, it is very fast measurement and very fast we can able to set it up. In a simpler way, the Precitech machine can able to produce one component in 2 or 3 minutes. For measurement, I cannot take like 20 minutes. So I need to measure within that particular time, as much as possible faster I can able to measure it, so that we can reduce the idle time of the manufacturing machine, so that it can give the feedback at faster level, and then we can start producing the next component, so that the utilization of the machine, manufacturing machine, will be more. So that is the idea behind it. And it is not only the fast, at the same time, very important is very accurate or precisely we need to measure it. So it's combining managing the both fast and the accurate measurements. And it is a fully automated machine. So there is no much skill is required. We can able to make or generate program, automatic program. So the next time anybody can just execute the program, something like a CNC program. Just press a cycle start, and then it is going to start. And even the alignment is also we can able to automate. So just load the component on the chuck, depends on the component, we can make a fixture and just load it. Alignment, measurement, analysis, all can be automated. So again, the accuracy wise, the capability of the machine is we can able to measure up to a 300 millimeter diameter. It's a bigger diameter part. The sag in the sense it is a depth. We can measure up to 50 millimeter depth. It could be a concave or it could be a convex. Either profile can be able to measure it. The spatial frequencies is 125 nanometers. As I said some few minutes back, it can collect 8,000 points per millimeter. The calculation is from here. So it picks up every 0.125 microns or every 125 nanometers, 1 point in x-axis. So in millimeter, roughly about 8,000 points. So, and the repeatability or the accuracy, we can say it's less than 50 nanometers. And the very important parameter of any machine, what is the inherent error or what is the noise of the system, basically. So it's very well defined. It is less than 2 nanometers is the inherent error of the measuring equipment. So example, I'm looking for 50 nanometer form error of from the component from the manufacturing machine. So my measuring equipment should be at the lowest level of the error. But I cannot eat away 50% of the tolerance which component produced from the manufacturing machine. So if my component is produced at the level of 50 nanometer accuracy, my error is just a 2 nanometer, which is not in a big numbers, which is just we can it is a negligible amount of error. But the 2 nanometer error, it is a cumulative of mechanical, electrical, electronics, whatever the error, any form of error will be generated from the machine. it should not be more than 2 nanometers at any point of time. So we have a masters to prove it. So it will be proved during the installation of the machine. So we have a traceable, internationally traceable master to prove this kind of accuracies. Yeah. And anyway, it is a ISO compliant output. We follow the roughness parameter or the form error analysis parameters, the algorithm whichever we use in our Taylor Hobson defined software. We follow the ISO standards, and what standard we are following all is a part of our report. We can able to change, say some example, somebody from Japanese customer, they are trying to use a G standard. The software, we can able to switch over from ISO standard to Japanese standard, which is G standard. Then the analysis or algorithm is automatically will change as per the G standard. And similar way, if somebody from Europe, they can very well follow the VDI standard or their German standard. The software is very flexible, very flexible. We can able to change the standard according to the user requirement. And we have the advanced analysis packages like aspherics utility. So if we are generate not just a spherical form, we are going to generate something like aspheric or diffractives. There are some additional software capabilities are available to remove the aspheric form, and we can able to find the exact form error left out in the sample. In other words, we have some sample like aspheric or diffractive form sample, but we don't have any design. We need to generate from the aspheric coefficient. That is very much possible from the machine. Without knowing anything, you can just leave the machine and then just trace it. The software can be able to generate the aspheric equation for 10 order, 12 order, 20 order. We can able to generate it, and the base radius and what is the conic constant, all can be able to generate. That is called a reverse engineering. That also is very much possible by the PGI with the usage of AAU software. Yeah. So I have few video. I can just run it for you. Can you able to see the video, Dr. Rajesh?
No, sir. No, sir. Not yet, sir.
Not yet. And just confirm when can you able to see.
Sure, sir.
Yeah. You want me to stop that PowerPoint and then open it again, or how it works?
That it is better, I think, sir. You can stop
I'll
this
just
presentation, and you open that video, then share the window, sir.
Sure.
It may be working.
Probably now you can able to see it.
Yes, sir. It is coming, sir.
Yeah. Okay.
Yes, sir.
So this is the contact profiler. The stylus tip, as I said, it is made up of a diamond material, and we have a multiple small lenses. We can able to measure it all in a single setup. So that is called a matrix. You can have a n number of sample within the measuring volume of the machine. So there are three, any number of, if depends on the size of the sample. So in this example, we have about 8 sample. So you can measure the 8 in a single setup, and we can have the error map of individual 8 sample in a single page report. So once the component is over, the measured, the stages we have a Y stage to move it and position the next sample near to the stylus so that it keep measuring it. Yeah, this measurement is over. Next, the sample will move and position the next sample near to the stylus so that it keep measuring. So it is going to measure the all the samples wherever it is loaded on the part. I'll just quickly run the video. Yeah. So this is how the measurement. This is the actual cycle time of the 8 sample measurement. And once it is done, the analysis is going to be automatic. And we will, in a second, we can able to get the error map, and then it can able to give the feedback to the diamond turning machine to correct. If it is any form error, which is not acceptable as per the requirement, we can able to correct it. Or if it is acceptable, we can continue the production. So that is what the idea is. So the next, I have one more video of free form measurement. So why it is measuring the ball? It is to locate the position of the fixture. That is my reference. The balls, it is fixed position. That is the reference. From there, it will find out where exactly I'm placing the part in the middle. So it is a multiple 2D traces at a certain distance, and the distance can be defined before measurement. What is the distance for the each measurement? You can define in microns, every 10 microns, or every 1 millimeter, or every 5 millimeter. That can be defined before. So accordingly, it will move, and then it can able to measure and then generate a 3D surface of it. So it is covered the entire portion of the surface. Yeah. Yeah. So unfortunately, the result we couldn't able to share it because the part is the customer specific. So we may not able to share the reports because there are a lot of confidentiality for the results and sharing the customer name and the application kind of thing. So it is just a concept how the contact profiler measures the optics. Right. So if you have any questions, then you can quickly ask, because I'm going to move to the next topic of non-contact measurement.
Thank you, sir. Sir, we will take at the end questions, sir. Better you can continue.
Right.
Yes, sir. Thank you, sir.
So I'll just. Yeah, can you able to see my PPT now?
Not yet, sir. Yes, sir. Coming, sir. Coming. Yes, sir.
Right. So now we are going to see a non-contact solution, measurement solution. The machine name called a LUFOSCAN. So, and again, we are try to get the best possible of the contact profiler, the concept. So it is a single point non-contact sensor instead of touching the surface, because the latest trend are moving high precision optics. Most of the customer, they don't want to touch the surface by any form. not even by the stylus, not even by the hand, not even by finger. Any form, they don't want to touch the surface, because in the nanometric surface, definitely it will going to spoil at a few nanometer level. So they prefer a non-contact solution to measure it without touching or without scratching any surface. So the non-contact sensor, it is based on the single point laser, and again we are trying to measure a 3D surface, which the entire volume of the surface needs to be covered, and we can get a 3D error map or 3D surface profiles. Correct. So we can able to stitch in that. I can able to explain it how it measures, and I have few example videos of probably I think I have one concave and one convex. So you can see both how it measures. So this machine is a combination of the contact, means the single point non-contact probe, but the concept is from the machine, and the other side is the 3D metrology. We need to measure the entire surface, like Murugesh sir explained, the 3D surface, how Zygo will come into the picture to measure it. So the LUFO scan now can able to measure the entire 3D surface or 3D profiles. Yeah. Right. So what kind of profiles it can measure, the LUFO scan? You can see the machine, the size of it. It is quite compact. So it can be placed very next to the manufacturing or precision diameter machine. So if we have a steep spheres, axicons, any kind of sphere in concave or sphere in convex, or multifocus lenses, freeform and camera molds, segmented spheres, mainly as for diffractives, annular lenses. So any kind of form, we can able to measure it in the non-contact LUFO scan. So this is more into the dimensions. For example, if it is a 260 HD, means we can able to measure up to 260 millimeter diameter. It is the 260 is defining the diameter of the sample, mainly the accommodation of the sample. So up to 260 we can able to do it, and 420 is 420 millimeter diameter. And recently we manufactured one machine that is a custom specific 800 millimeter. It's a big optics supplied to one of the customer in China. The accuracy of the machine is plus minus 15 nanometers, which is the best at the moment in globally. For this error is for the entire 3D profile error, not a single trace like what contact profiler does. It is a 3D error of plus minus 15 nanometers. Yeah. So the machine concept is this is a conceptual picture of it. So this is a C. You can see wherever it is mentioned. It is a rotary stage. It is a pneumatic. Is a air spindle. So which will rotate in RPM up to 100 RPM. We can define the RPM based on the requirement of the profile accuracy. Say example, we are going to cut some sample. We know that this is the rough sample, rough cut, and it is not a finished sample. My error will be in the order of 200 to 300 nanometer. Probably we can able to rotate very speed up to 100 RPM or 90 RPM, and we can able to measure it. And if you are looking for something like 25 to 30 nanometer form error, probably we need to reduce the speed maybe around 25, 30 RPM, and we can able that can be defined. That is the important of it. We can able to define it before we start the mission. And the R is the arm axis. The axis can be, it's like X-axis movement, and Z is the up and down movement. And the T is the swelling of the probe. So the concept here is that the probe is always normal to the surface. You can see the below picture. The laser beam is always, it is a normal to the surface. Say example, you have a concave shape, and the radius is the contact point is going to change each and every time, and the probe will tilt according to the radius of your sample. So in the sense, we need to define what is the radius we are going to measure it, and what is the form shape. It is a concave and aspherics. We need to define everything before starting the measurement. So the probe, the optical probe will tilt each and every time when the spindle rotates, and accordingly to the part normal to the surface, it keep tilting. It can tilt up to 90 degree, so that we can able to measure even the steep slopes or even the hemispheres. We can able to measure from the 0 degree to 90 degree horizontal, so that we can able to measure the entire hemisphere. Yeah. So this is how the probe is going to release the laser beam, and there is a receiver which can receive the laser reflection from your sample, and the spindle is going to rotate, and the probe will move in only one axis, which means it will take a spiral scan and can collect the entire optics 3D surface. You can see the example how it measured. This is the heat plot or 3D plot of the measurement. Yeah. So this is the same concept what I explained it. So one of the very important point, how we achieve the accuracy of the measurement. From even the axis is moving, X-axis and Z-axis is moving, the probe is tilting, the spindle is rotating. There are so many motions during the measurement. The key point here is the machine, the movement of each axis follows the Abbe principle. So what is Abbe principle? It is very simple. Example is vernier caliper and the micrometer. I hope most of you people used the micrometer and the vernier caliper. So vernier caliper, I am trying to measure some diameter of the ball. For example, the ball, it's held between two jaws. You can see the ball diameter is clearly different. It's a bigger in size, it's a smaller in size, but the result is the same. How? Why? Because the measurement and the scale, measuring scale is not in same plane or same axis. If the jaws is not parallel to each other, it is the jaws got bent or something, so it is not going to read the exact scale, because the scale is not in the same plane. So example here in micrometer, the measurement and the scale, where we can able to see the results, it's in the same plane. So there is no multiplication factor or whatever. So there is no calculation. It's a straight displacement. Whatever the diameter, according to that, the scale will get displaced. We can able to see the results. So that is called the Abbe principle. So we follow each and every axis, X-axis and Z-axis, and the probe rotation, all axis, the scale is fitted in the same plane of the axis movement. That is why it is more accurate. And addition to that, the material frame or the axis frame, it is made up of inward material, which you definitely will be knowing it. That is temperature wise, or it is very stable material for against the environment. So any temperature changes, the inward material, the thermal expansion is very, very, very minimal, which is negligible. That is why we use that material for all the frames, axis movement frames. So these are all few reasons why this machine is producing high precision results. There are n number of reasons behind it. So I just considered only one or two main points to focus it. Yeah. So this is about the machine. And so this is anyway, it's available in the brochure or any presentation. It is how much is the volume size of the machine and what kind of chuck we use and what is the spot size of the laser. It's a 4 micron. So okay, so it's a very, very tricky point here. The 4 micron, we use a spot size. So we are focusing in this LUFO-scan mainly the form error of the optics. So we are not focusing any surface roughness here. Surface roughness will be measured in the contact profiler. Here we mainly measure form error in a very faster machine. The stylus, if it moves, we have limitation for the movement of the stylus. We usually recommended movement speed is about 1 millimeter per second. So that is what the speed. So example, if you have a 100 millimeter diameter part, it is going to take 100 seconds, roughly more than 1.5 minutes, even the measurement time. So the alignment time, loading and unloading time, all is going to be added. But as I said, in this LUFO-scan, it is going to rotate 100 RPM. I'm sorry, the profile, contact profiler, it is going to measure 1.5 minutes in a single trace. It's only one line. So if you are trying to cover the entire 3D surface, it is going to take more time, probably 15-20 minutes. But in the non-contact, there is nothing is going to touch. So we have no limitation of the speed. And unless we get a very good data from the machine, we can able to rotate any speed. So if it rotates 100 RPM, like a 100 millimeter diameter part, probably we can able to measure it within 2 to 3 minutes for the entire surface finish. That is the major difference and major advantage against the contact profiler to the non-contact. Yeah. So I have a few measurement videos. So the part is loaded. This is the air spindle. It is rotating probably about 80 RPM in this machine. You can see the probe is tilting according to the radius or according to the profile of the part, and it always the normal to the surface. This is actual measurement video. This is not a speed. It is just a 1x speed. So this is what the cycle time it is going to take to complete one measurement. So it is a single point, and it moved only one side, and during the rotation of the spindle, it is covered the 360 degree, and it is like a spiral scan. So it takes it collected the data for the entire 3D data. So this is approximately the slope is about 63 degree. Still, we can able to measure the entire surface, but this is maybe the limitation in the contact profiler. We may have to tilt the sample, or we may have to tilt the traverse unit. So here we no need to tilt anything because we have a tilt option in the probe itself. So the probe can tilt according to the slope of the part and can able to collect the data. And this is example of aspheric profile. The diameter is about 50 millimeters. Just run. You can see the profile in the top, the scale. So that is how, because it's an internal, you may not be able to visualize it, but the profile, it's different. So you can see how the probe is rotating according to the shape of the profile. Yeah. And this is not the actual cycle time. It is run faster because we run the video very fast. It's a tricky profile, so it rotate very slowly, and the rotation of the probe is also very small, and it is a high accuracy part. So we rotated the spindle and rotated the probe at very slow speed. So, but it takes almost 3.45 minutes to cover the entire part. But still, 3.4 minutes to measure the entire 3D is not a bigger time. It's still very fast. That is to explain to you. So I just run the video in the faster. And so the standard machine can measure any kind of surface like concave, convex, asperates, diffractives, and flat especially, and mainly the measurement. If you look at the video, it started from the center of the spindle. So the component, the requirement should be a rotationally symmetric. So if it is a rotationally symmetric, any kind of profile can be measured in the loofah scan with the standard machine itself. And I have some statistical data how accurately we can measure it. So we had a 25 millimeter diameter test calibrated sample, which is calibrated in the internationally traceable laboratory, which is the US laboratory. So we tested almost 5 times. Take the part and put it back, and we have measured it. And you can see the difference of 5 measurement. It is just 0.7 nanometer, which is less than, which is the RMS value, which is less than 1 nanometer. And the PV, these are all the parameters which customer morely they're into, PV 99 and power. So PV 99 is one of the very tricky parameter. All the customer measure it. All 5 measurements, the results is less than 3 nanometers. And it is not a one machine, one place. We have taken the same master. We have one more machine, the same similar machine in German laboratory. So we brought the same sample and measured it on the machine which is installed it at Germany office. So this is the combination, this is the consolidated report of the variation of both the machine. It is not related to one particular machine and one particular time. And we have to ship the part from Japan to Germany. So it takes few weeks to go there and load on the different machine, measure it couple of times, and the time period will be different. So which means the results is very stable across the time. Results is very stable any of the loofah scan machine. So that is how we prove the accuracy of the non-contact loofah scan machine, which is very, very stable and very accurate and very repeatable and very reproducible. So these 4 points are very important for any machine. Right. So these are all some of the example. I got it. We have measured from the customer sample. This is the segmented optics. which can be measured. We have measured it on the LOFO scan. And the second is the annular lenses. So the annular lenses have few limitations on the contact profiler because it has got a hole in the middle and the thickness of the sample is very less. It's like in 1 millimeter, 2 millimeter. It's like very films. So we always have because the contact is going to touch, and we should have a proper vacuum check kind of thing. But in non-contact, nothing is going to touch, so there is no force acted on the sample. So it is always preferable for the filmy sample on the non-contact principle. And AICTE samples, because it has got a steep slope, so it will have few limitation on the contact stylus angle. It should not fall on the AICTE angle, so it will be lesser. The AICTE angle is like a 90 degree, so we need to select the stylus which is less than 90 degree, probably 60 degree. But it's a straightforward application in the non-contact. We will not have any limitation. And as for diffractives can be measured. And so these are all the applications are the solutions available in standard. Any of the LOFO scan can be able to produce, can be able to measure this kind of whichever I showed it. But we have some peculiar example of the free-form sample. So free-form, as I said, it's a free-form. So it can be anything. It can be customer specific requirement of angle. So we can able to generate or make a specific software for the free-form measurement, and we can able to make a special request probe for the free-form measurement. So there are custom specific modules are available that can be offered to any of the customer based on the free-form requirement. Yeah. And so mainly the free-form, if it is plus minus 5 degree slope of the free-form, it can be standard probe can measure. So standard probe can measure, but the software you need customer need any specific analysis for the free form, we can able to generate only the software part of it, but the standard probe can be used. The other side, they have a free form sample itself, it's more than plus minus 15 degree slope. My standard probe will have a limitation. So we have a special probe to cover the steep slope of plus minus 15 degree. So that can be added into the machine, and straight away they can able to measure it. So this is all depends on the application, depends on the requirement. So we have a different solutions to cover or to fulfill their this is what one of the example of free-form measurement. The tangent slope is less than plus minus 5 degree. We call it as a mild free-form or lesser free-form effect. So the standard LOFO scan machine and standard probe can able to measure it. If it is more than 5 degree up to 15 degree, so we may have to we may need a special HNA probe. We call it HNA means high numerical aperture probe, which will go very closer to the part so that the slope will be minimized. It can able to collect the reflection from the sample or from the optics, and then it can able to analyze it. So this is what this it's a special or custom made solutions available for the free-form measure. Yeah, hopefully I covered all the topics. Yeah, probably I'm on time or still waiting.
Yes, sir. Yes, sir. Time it is up. Exactly, sir.
Yeah,
Sir, now shall we go with question and answer session, sir?
Yeah, please. If we can unmute it and then ask for the question,
Yes,
we can start it. Yeah.
yes. I request, dear participants, you can unmute yourself and you can ask the question directly to our resource person, or you can type question in chat box. We will ask on behalf of you.
Sir, well, Murugan sir, excellent presentation, sir.
Thank you very much.
Because this what we do not know, the industry is going to nano level, and you have explained very well, sir. My question is, sir, can you throw some light on this online calibration, sir? I think you have mentioned somewhere in your screen, in your slides, sir.
Yeah, calibration. There are two things here: calibration of machine or calibration of masters. There are two things. So one is usually we have a calibrated masters. Using the master, we calibrate our machines. The master is playing a major role. So we should have a internationally traceable result for the master. Then only the calibration of the instrument will be valid. So we have a lab, CMTI, which is in Bangalore. So they have a very good facility to calibrate the masters. It can be calibrated. We have a setup in our Taylor Hobson facility at Leicester in UK. We can calibrate it. So using the calibrated master, using the calibrated results, we can able to calibrate and prove the machine at site or online. Yeah.
Thank you, sir. Thank you, sir.
Dear participants, you can unmute yourself and you can ask questions. Sir, shall we go with the vote of thanks, sir?
Yeah, if you have any questions, maybe later on you can write a mail to Dr. Rajesh, and he is having my email ID. Definitely we will get back to you with the correct answers.
Thank you, sir. Thank you, sir. Sir, we are getting the overwhelming responses, sir. Nice presentation. Sir, just 2 minutes, sir. I will finish my vote of thanks, sir. Thank you for your wonderful presentation, sir. You have explained the application of latest technology, manufacturing, particularly measuring instruments, assisted machine tools. The takeaway from your presentations are very high. You have started with phase grading interferometer, industry leading capability like fast measuring, accurate within less measuring time, and explained the video like a Taylor Hobson stylus contact measuring instrument and non-contact lenses, LUFO scan, single point sensor, and its measurement applications, and measurement principle like a reference frame concept and AB principle, and relevant specification you are given for LUFO scan. LUFO scan measurement, some standard measurement like ASPS, spheres, and particularly you explained the reproducibility of LUFO scan, and explanation of annular lenses and any freeform, particularly custom designed models you have explained. Thank you very much, sir. Really, it is a useful information what we have received. Thank you very much, sir. Now I request our Professor Chandrasekhar Reddy, sir, to conclude the session with vote of thanks to the resource person, sir. Our
Sir,
convener.
is audible?
Yes, sir. Yes, audible, sir.
Good afternoon, sir. Good afternoon, Velu Murugan, sir.
Thank you, sir. Yeah, good afternoon.
On behalf of management, principal, Department of Mechanical Engineering of SVCE, and the participants of STTP, thank you very much for accepting our invitation and delivering an informative and thought-provoking webinar on optic solutions organized by SV College of Engineering, Tirupati, in spite of your busy schedule, because you are all industry people and all industry people. We have a busy schedule. In spite of your busy schedule, you came to us and you are spared your valuable time, sir. Thank you.
Yeah, it's our pleasure, sir. Thank you.
Thank you very much, sir. Thank you, sir. Dear participants, our today morning session ends here, and we will start the next session, afternoon session. Time is 2 p.m. It is from Professor Mary Esther from Umbeldian Scientist, University of Munster, Germany. The topic is functional behavior of oxide thin films and characterization challenges for smart and futuristic applications. I request all the participants please join 1:45 p.m. itself so that we can start the session exactly at 2 p.m. Thank you all. Thank you very much.
Madhuvanan sir, is there any
Yes, sir.
feedback? Last
Yes, sir.
feedback,
Sure,
because
sure,
it is
sir.
third day, I think so. We completed
Yes, sir.
3 days. So
Yes,
remaining
sir.
3 days. So
Yes,
any
sir.
feedback, they can unmute and then they can tell the feedback.
Sure, sir. Thank you,
If
sir.
you have any problems or the constructive and feedback, or if you have any problems also, they can tell.
Okay, okay, sir. Thank you, sir. Now I request dear participants, if you can add your suggestions or if you can add your feedbacks to us so that it will sharpen our effort and we can improve further. I request you share your feedbacks, sir. Dear participants. Sir, one feedback from Professor Vaibhav. I request organizers not to post the same links again and again. Feedback link, sir. The problem is participants are asking continuously, sir. Sometime what happens, no, they have left the meeting, and if they are joining, no, there is a chance that they will not get the link. So they keep on asking again and again. That is the reason we are giving this link. Okay, 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 sir. Yes, sir. This is the reason. Any other feedback, please, sir. And another feedback from Professor